Welcome back. We will now have a lab session, in fact a tutorial where we will look at generating various kinds of network models. And let's see how to go about, say, the Erdős-Rényi model, the Watt-Strogatz model, and so on. So I'm doing this in a Jupyter notebook. The notebook has already been shared with you, and you can also execute the codes in parallel and see how this works. We typically start with importing all the necessary packages. We import NumPy, Matplotlib, NetworkX, and so on. So let's just run that. Okay, there is just a simple deprecation warning which we can ignore for the moment. And then we look at generating an Erdős-Rényi graph. So let us just look at the code here. So this is a GNM model, right? There is also a GNP model we can have. So recall what is the GNM model. You have n possible, you have n nodes in the graph, and out of the n choose 2 possible edges, m of them happen to exist. M of them happen to be connected. M of them are actually connected in one random realization of the Erdős-Rényi graph. We can have multiple such realizations and then look at various properties and how these things change with respect to what is the distribution of these properties and so on. You can essentially build an ensemble of networks and then study how various properties are distributed. This is like a classic bootstrapping scenario. So what are we doing here? We are just picking m random edges from a total possible of n choose 2 edges, right? And let's just run this. And that was quick. So, and now let me try to generate this. Now this is now an Erdős-Rényi graph with 50 nodes and 20 edges at random. So let's just change this to just 2 edges and just see that it happens. You have 2 edges, so connecting 0 to 14 and 0 to 19. And now we have 2 edges that connect 24 to 30 and 22 to 37. And so on. Now let's add a few more edges. This is going to look quite messy. Yeah, it's really dense now, right? And now you will see that the various properties have really changed. If you look at the average degree of this graph, it's going to be much higher than what you had in the previous scenario. Okay. You can also generate an Erdős-Rényi GNP graph. So what is the logic that we use here? It's very similar to the previous. So here all edges is np dot array list of combinations of range n comma 2. Same thing here, and then here you already picked m edges from all possible edges. So what you do here is you see which of the edges have land. So you generate n choose 2 numbers in 0 comma 1 and you see which of them are less than p, right? And whatever is less than p, you again make those connections. So you're going to expect something like how many edges? You're going to expect something like m by n choose 2. So p is going to be so p is you basically pick p as m by n choose 2. So you basically do p into n choose 2. That's going to be the approximate number of edges. So let us just pick this and do with 50 and 0.01. Let's just run this. Let me run this function in the first place and then run this. Yeah, I get this. Now let's make this. So n choose 2 is going to be something like close to 2450 or something like that, right? So it's going to be 2450. So 1 by 2450. Let's make this 2 by 2450 and run this. So you have only one edge here. You have no edges this time. No edges. Two edges. One edge. Two edges. No edges. Two edges. 2, 0, 1, 1. So you see, right? So sometimes you have as many as 3 edges. Right? The probability is the same, but then you're going to get different kinds of networks. When you had NM, you have the exact same number of edges, no matter what you do here, right? So let's put it as 4. You can see the 4, 4 again, 4, 4, and those. I don't know if that was probably overlapping. Let's see if we find that again. This should also be 4. Maybe it's good to just debug this. So let's print four, 4, 4. This looks like 3. Okay, this also is a 4. Yeah. Yeah, I think I may have just missed that. So there is. Okay, this I was convinced was 3, but then you see this tiny teeny edge between 6 and 7 here. So you can see that this is pretty consistent, right, in the number of edges that it generates. Whereas here, there's going to be a distribution of the possible edges that you generate, but it's not going to be, but when you put some reasonable numbers like 0.01, you're going to get comparable output. So now let's plot the degree distribution of the ER graph with n equals 10,000 and p equals 10 to the minus 3 and 10 to the minus 4. How does it vary? Okay, so we're setting n and p as 10,000 and 10 to the 4 and 10 to the minus 3, and we are generating obviously the NP ER graph that you see here. Let's go. So this is sort of degree distribution that you see. It seems pretty much Poisson in nature, and you can try this with a different value. Yeah, and now you get a slightly different degree distribution. You can still be able to fit a Poisson degree distribution, but you can also fit a binomial and so on. And let's make it even larger, a little more challenging to compute. This almost looks normal, right? But you can see that you can always fit a binomial here, which is what it is, and in a continuous case you should be able to fit a Poisson distribution. So I hope this gives you a good picture of what's happening here, and you can do it for different values. So here you go for 10 to the 4 and 10 to the minus 4. You see a sort of arbitrary spike at 7 for whatever reason, but yeah, maybe you run it again, you will get something completely different. Let's run it again. It does take a bit of time to run. So one could see if there are ways to speed this up. Yeah. You do again curiously get that spike at 7. But yeah. Okay. So I hope that gave you a good picture of building ER models, ER graphs of two types, both NM and NP, using network X and NumPy. Okay. So now, because this becomes very essential, so this is central to any kind of ensemble generation that is needed for you to compare the properties of your real network with these random networks. So what is the background expectation? What is the clustering coefficient that you would expect at random, and is it what you find in your real network or it's much higher? So these kinds of questions you can answer by building these ensembles using the kind of ER graph code that we saw here. So hope this helps you.